This is Eric Worm. I'm the Program Director of the Internal Medicine Program at the University of Cincinnati, and today I'll be presenting Acidbase 101. After this presentation, you should be able to diagnose single, double, and triple acid-base disorders. I give you 7 steps to acid-base nirvana. Step 1, note the clinical presentation. Step 2, check internal validity using the Cassirer-Blake equation. Step 3, determine the anion gap and osmolar and urinary gaps if indicated. Step 4, draw the arrows, something I will show you in a few minutes. Step 5, apply the rules of compensation. Step 6, if compensation rules cannot be satisfied, determine the nature of the mixed disorder. And Step 7, calculate what's called the delta-delta. Let's begin. Step 1, note the clinical presentation. Most clinical situations are associated with predictable acid-base disturbances. You should be able to predict the acid-base disorder once you review a case given the history that you're given. If your interpretation of the acid-base disorder doesn't match your prediction, you may be missing something, or your interpretation of the numbers isn't correct. Take, for example, metabolic acidosis. There are many causes of an increased anion gap metabolic acidosis. There's a classic mnemonic called mud piles. You can stop this presentation and review those things under each of these categories if you wish. A non-increased anion gap metabolic acidosis also has a broad differential diagnosis that you can remember. Metabolic alkalosis has a category known as chloride responsive or low urinary chloride. You can see the things that cause that here. And chloride unresponsive, which also has a differential diagnosis. Again, if you need to stop the presentation to review this, please do so. Respiratory issues are pretty simple. A respiratory acidosis is caused by anything that stops or slows breathing, and a respiratory alkalosis is caused by anything that makes breathing faster. Step 2, calculate the Cassirer-Blake equation. It's also known as the Henderson equation. As you see, this equation is the hydrogen ion concentration equals 24 times the partial pressure of carbon dioxide over bicarbonate. It's the ratio of dissolved CO2 to bicarbonate rather than the actual concentration that determines the hydrogen ion concentration and thus the pH. This is very important. It's a ratio, not a set of absolute values. We'll come back to this in a few minutes. Here's a pearl. If you try to remember this equation, one way to do that is remember that the hydrogen ion concentration equals 24 acid divided by base. The way I remember this is think of Mr. Henderson doing 24 sit-ups on the ab roller. 24 over acid base. This helps me. I hope it'll help you. Why should you care about this information? Well, the bicarbonate on most blood gases is calculated from the hydrogen ion concentration and the PCO2. So using this information, the Cassirer-Blake equation always works. The bicarbonate you should use to diagnose acid-base disorder should be the measured level on the renal panel. If the blood gas and the renal are drawn far apart in time or are altered in the lab, they might be representing different metabolic states. Therefore, you may not be able to solve the Cassirer-Blake equation or make an accurate acid-base diagnosis. One shortcut is to compare the bicarbonate on the blood gas to the renal panel to see if they're close, because that's sort of an approximation of the Cassirer-Blake equation. However, be careful with this. I would encourage you to do the equation, which I'll show you. You're probably wondering, how do you calculate the hydrogen ion concentration when you're just given the pH? Well, the way to do this is that from between 720 and 760, the hydrogen ion concentration equals 80 minus the last 2 digits of the pH. So if the pH is 7.32, the hydrogen ion concentration is 80 minus 32, the last 2 digits of the pH. In this case, it'd be 48. Now this works great when it's in this range between 720 and 760. But if it gets outside this range, you might want to use this equation. For each increase in the pH of 0.1, you multiply the hydrogen ion concentration by 0.8. And there's the example here. And on the other end of the spectrum, for each decrease of 0.1 unit, you can multiply the normal hydrogen ion concentration by 1.25. And you can see the example here where it's 7.30 is 0.1 unit below 740, so it's 40 times 1.25 equals 50. These are some equations that you can use to calculate the hydrogen ion concentration. Let's look at example problem number 1. Say a blood gas and a renal panel are drawn at the exact same moment, and the blood gas is sent to the lab, but not on ice. And then the tech accidentally places the blood gas in front of a heating vent and runs the sample at some point later. Here's what you get. In this case, the pH is 7.26, PCO2 is 55, the bicarb that's calculated is 11. On the renal panel, the bicarb is 31. If you tried to calculate the hydrogen ion concentration, you would take 80 minus the last two digits of the pH to get 54. Try to solving for this equation using 24 over acid over base, that's the ab roller there, acid over base. You ask yourself this question, does 54 equals 24 times acid 55 over base 31? And the answer is it doesn't. It doesn't calculate, because in this case the bicarbonate is really low because that thing was kind of heating in front of a vent and probably turning to acid on the vent. The bicarbonate is getting buffered in solution and it goes down. And so at this point you cannot use this information, and you must redraw the blood gas in the renal panel at the same time and run it correctly, because you cannot proceed any further with this example. Now a couple of terms you need to know. Acidemia versus alkalemia. These terms represent the abnormal hydrogen ion concentration in the blood. Only the pH determines this. A normal pH for the examples that I'm going to share today is between 7.35 and 7.45. Other labs may have different numbers, so you may want to check them out. Acidemia, therefore, is a definition that the pH is less than 7.35. Alkalemia, the pH is greater than 7.45. Here's something that's really important. You can only have one emia at a time. You either have acidemia or alkalemia. It's measured on a blood gas. If you look at a renal panel and you say there's anemia and you don't have an actual pH, you might get yourself into trouble. Now here's another set of terms. Acidosis versus alkalosis. These are abnormal states which, unopposed by therapy or disease, would change the pH from normal. These are defined independently from the pH. So an acidosis is a primary process which, if unopposed, would produce an acidemia. So if you let it go and didn't do anything about it, you get a low pH. An alkalosis is a primary process which, if unopposed, would produce an alkalemia, which means if you let it go, it would cause a high pH. You can have several, quote, osises at the same time, thereby allowing for mixed acid-base disorders. That's how you can get a metabolic acidosis and a respiratory alkalosis, because these are just processes, these are tendencies that eventually drive one way or another, but are not necessarily represented by the pH. So here is the Kaiser-Bleich equation, represented now with the pH being the inverse of the hydrogen ion concentration. In a respiratory acidosis, the PCO2 rises. You're not breathing, you're retaining PCO2, you're retaining acid. When that happens, the ratio between the PCO2 and the bicarbonate goes up, so the hydrogen ion concentration goes up and the pH goes down. That's an acidemia. In another example, in a respiratory alkalosis, you breathe quickly. You breathe the PCO2 off. The PCO2 to bicarbonate ratio drops. The hydrogen ion concentration drops. The inverse relationship of pH, that goes up. You have an alkalemia. Another example, in a metabolic acidosis, bicarb goes down, either buffered or lost out of the body. When that happens, the ratio of PCO2 to bicarbonate goes up. The hydrogen ion concentration rises. The pH drops, and you get an acidemia. Finally, in a metabolic alkalosis, the bicarbonate goes up for whatever reason. When that happens, the ratio of the PCO2 to the bicarbonate drops. The hydrogen ion concentration goes down. The pH goes up, and you have an alkalemia. Step 3. Determine the anion gap. This is one of the most important concepts to know when you're dealing with acid-base disorders. The anion gap is the sodium minus the chloride plus the bicarbonate. And for our examples today, that gap will be normal at 12. This is based on the theory of electron neutrality, that all the positives in your body have to equal all the negatives in your body or something really bad happens. It just so happens that there are lots of positives and negatives that are in our body, like calcium, magnesium, and potassium on the positive side, albumin, sulfates, phosphates, lactate, other things on the negative side. But in the anion gap, we're only measuring some of the positives, in this case the sodium, and some of the negatives, the chloride and the bicarbonate. One pearl. Because albumin accounts for most of the normal anion gap, the anion gap value should be adjusted downward for patients with hypoalbuminemia. The approximate correction is a reduction in the normal anion gap of 2.5 milliequivalents per liter for every 1 gram per deciliter decline in the plasma albumin, if the normal value is 4. So let's take the case of an increased anion gap metabolic acidosis. In this case, what happens is that bicarbonate is replaced or buffered by other negatives. A negative takes this place, with an increased anion gap, metabolic acidosis. When the bicarbonate falls, the product between chloride and bicarbonate is decreased, and anion gap goes up. In a non-increased anion gap metabolic acidosis, bicarbonate is lost, usually through the renal or GI tracts. In this case, a negative has left the body and is not replaced by another negative. So the body does something smart. The kidney says, you know what, I'm going to hold on to chloride. And for every drop in bicarbonate, the kidney retains a similar amount of chloride, another negative, and the anion gap does not change. Let's take the case of a metabolic alkalosis. In this case, you've gained bicarbonate for whatever reason. Perhaps you drank a lot of milk. In this case, you've retained a bunch of negative. The kidney, being smart, says, you know what, I don't need all this negative hanging around. I'm going to get rid of a negative, and the negative it gets rid of is chloride, and the anion gap does not change. What's cool about metabolic alkalosis is you can come at it from the other way. Let's say that you lose chloride, for example, by taking a bunch of Lasix or diuretic. In that case, the kidney says, well, I lost this chloride out. I'm going to retain another negative, in this case, the bicarbonate, and the anion gap doesn't change. It can come from either direction. Either way, you get a metabolic alkalosis without a change in anion gap. There's another gap you should be aware of. That's the osmolar gap. Plasma osmolarity is 2 times sodium plus glucose divided by 18 plus BUN divided by 2.8. The osmolar gap is the measured osmolarity minus the calculated osmolarity. In patients suspecting of poisoning, for example, I've got pictures of antifreeze here, a high osmolar gap, particularly if it's greater than 25, with an otherwise unexplained high anion gap, metabolic acidosis, is suggestive of either methanol or ethylene glycol intoxication. So in specific cases, you may want to calculate the osmolar gap. Another gap you should know about is the urine anion gap. This is calculated as sodium plus potassium in the urine minus chloride. It's usually 0. In diarrhea, you have gut loss of bicarbonate, and excess acid with chloride is excreted, so the gap is negative, calculated like this. You get an increase in urine chloride, and what happens is that product goes less than 0. So one way to remember this, the mnemonic I like, is negative. So if the urine anion gap is negative, it's probably from a gut loss. On the other hand, in an renal tubular acidosis, where you have a renal loss of bicarbonate, the chloride is not affected. And so the urine anion gap is still 0. So if you can remember negative and 0 in urine, you'll be okay. Step 4 and 5. Draw the arrows and begin the compensatory response calculations, part 1. Here is something that's really important that you have to know. Compensatory responses never return the pH to normal or overshoot. The basis of the compensatory response is to maintain that PCO2 to bicarbonate ratio that I talked about earlier. Therefore, the direction of the compensatory change is always in the same as that of the initial change. So let's take an example of this, just break it out. Let's say you have that respiratory acidosis in which you tend to hypoventilate and retain PCO2. When that happens, as I said, the ratio goes up, the hydrogen ion concentration goes up, and the pH falls. Well, the natural response would be to raise up the bicarbonate, that's what the kidney does, to try to mitigate that rise in the ratio. And that's what happens. That's called metabolic compensation, and you get less acidemia. In a respiratory alkalosis, the opposite happens. You're losing PCO2, the ratio is dropping, the hydrogen ion concentration drops, the pH goes up. You get an alkalosis. The kidney says, well, I don't want this, so it offloads bicarbonate, and you get less alkalemia. In a metabolic acidosis, bicarbonate falls, the ratio goes up, the hydrogen ion concentration goes up, the pH drops. So what happens is you begin to breathe a little faster. You lower that ratio, and you get less acidemia. In a metabolic alkalosis, the bicarbonate rises, decreasing that ratio. So the hydrogen ion concentration goes down, the pH goes up, and you have an alkalemia. The response is to hypoventilate, to retain PCO2, to reset that ratio a little bit, and you get less alkalemia. Here's an exercise that I call draw the arrows that helps me when I'm solving acid-base problems. First, I'll draw an arrow where the pH is. In a respiratory acidosis, the pH tends to be low. The PCO2 is high, and that's the primary problem, as indicated by 2 arrows. So that's what's happening, is that you're hypoventilating, you're raising your PCO2, and it's causing an acidosis. The compensatory response is for the kidney to hold on some base to balance out a little bit of that acid that you're retaining. And because of the theory of electric neutrality, the chloride tends to be low. If you think about your COPD patients that you have, the next time you see one, check out their chloride. If they have chronic CO2 retention, you'll probably have bicarbonate elevated on the renal panel, and the chloride will be in the 90s. Respiratory alkalosis may be marked by a high pH. In this case, the primary problem is that you're breathing too fast and you're blowing off CO2, so that's dropping. The kidney then gets rid of some base to try to rebalance that ratio, and when it does that, because of the theory of electric neutrality, the chloride tends to be high. A case of chronic respiratory alkalosis is pregnancy. If you ever do a renal panel on a pregnant woman, you'll generally see their chlorides in the 105 to 108, maybe 110 range because of this process. For metabolic alkalosis, the pH tends to be high. The primary problem is retention of base for whatever reason. The compensatory response is to retain CO2, to breathe a little less, to rebalance that ratio. In this case, the chloride tends to be low because of the theory of electric neutrality. When the bicarb rises, the chloride falls. In a non-increased anion gap metabolic acidosis, the pH tends to be low. The primary problem is a loss or buffering of bicarbonate, usually a loss in a non-increased anion gap metabolic acidosis. In this case, the compensatory response is to breathe a little faster, to get rid of acid that way so that you can rebalance that ratio. In this case, the chloride tends to be high because as the bicarbonate falls and is lost out of the body, you tend to hold on to chloride to rebalance this acid, to rebalance the theory of electric neutrality. And the anion gap does not change. Finally, in an increased anion gap metabolic acidosis, the pH falls. Bicarbonate buffering usually is the primary problem. The PCO2 tends to go down as a compensatory response, but the chloride does not change because it doesn't have to. Because unlike a non-increased anion gap metabolic acidosis where you're losing bicarbonate out the body and holding on to chloride, rebalancing that anion gap, in an increased anion gap metabolic acidosis, you are buffering bicarbonate with another negative that you're not measuring, so the chloride does not have to change. Now what's cool about this, and here comes the draw the arrows part, that if you look at the metabolic problems, all the arrows tend to go in the same direction. See that? Either up altogether or down altogether if the process is working normally. In a respiratory problem, the arrows tend to split with the pH being in the opposite direction of the PCO2 and the bicarbonate. And what I do when I'm solving an acid-base problem is I just draw arrows next to each one of these things to get me started on what it might be, either primary respiratory or primary metabolic. So let's look at example problem number 3. A 45-year-old man drinks antifreeze. I'm going to tell you right now this is a case of an increased anion gap metabolic acidosis. So if we look at the values, you'll notice that the pH is 7.28, which is down. The PCO2 is 26, which is down. The bicarbonate is 12, which is also down. In this case, the anion gap is up. When you look at the 3 metabolic components, or the 3 components of the acid base, all 3 are pointing in the same direction. So you may say, I bet this might be a primary metabolic problem. The anion gap would indicate that it's an increased anion gap metabolic acidosis, but there's some more work to be done, which we'll do in a few minutes. But at least you know where to start. Maybe this is a metabolic problem. Another example, a 75-year-old woman with COPD. We'll just tell you this is a case of chronic respiratory acidosis. In this case, the pH is down, the PCO2 is up, and the bicarbonate is up at 32. In this case, there's no anion gap, but if you look at these 3 things, you'll notice that the pH and the PCO2 are driving in different directions. So when that's the case, you probably have at least a respiratory component. More work to be done, but it's a way to start. Step 6, solve for mixed acid-base disorders. Mixed acid-base disorders that make the pH normal are not compensating for each other. They are independent entities that just happen to balance the pH to normal. Never let yourself say the words compensate to normal. If something is normal and the other things are abnormal, you must have a mixed acid-base disorder. If you say compensate to normal, the people around you will know you do not know what you're talking about. So let's take an example. In a metabolic acidosis, the bicarbonate tends to go down. This tends to increase the ratio of the PCO2 to bicarbonate ratio, as you see here, and the hydrogen ion concentration goes up and the pH goes down. In a compensatory response, while you're lowering your bicarbonate, you tend to blow off CO2, get rid of acid in order to balance this loss of base or removal of base. In that case, you get compensation, which leads to less acidemia. Now, just imagine that you get a big bad PCO2 drop that's a lot more than compensation. Well, when that happens, it's possible that those ratios could put you right back to a normal hydrogen ion concentration and normal pH and no acidemia. But yet you could have both a metabolic acidosis and a respiratory alkalosis. I show two bullets at the top here because I want you to think about this. These two things are two independent entities, and if you can imagine when they come together that they're just pushing on each other, they're balancing each other, but they're not in any way compensating for each other. And if you remove one or the other, the bullet would then begin to fly. I like this metaphor. It works for me. Let's look in the other direction. Imagine if you have a metabolic acidosis as causing that acidemia that I described, and also a respiratory acidosis. These are two independent things where the bullets are going in the same direction. This usually leads to a really big acidemia, and if you're not careful, this patient is going to die. So think about each independent acid-base disorder as a bullet. Are they balancing each other out? They're not compensating. It's just lucky when they're balancing. When they're going in the same direction, you're in big trouble. Well, how do you know when you have a compensatory response and not a mixed acid-base disorder? Well, there are some formulas you should know about. So let's take the case of a metabolic acidosis. Again, the bicarbonate falls, and the response then is to drop PCO2 to breathe faster. And this is described what's called Winter's formula, that the PCO2 that you would expect should be 1.5 times the bicarbonate plus 8 plus or minus 2. This is known as Winter's formula. For example, if an acid load lowers the plasma bicarbonate concentration to 9, which would be pretty low, the PCO2 according to Winter's should be 1.5 times the bicarbonate, well, here it is 9, plus 8, plus or minus 2. That should be 13.5. Plus 8 gives you around 21.5, with a range of 19 to 23. In acid-base calculations, you often have this kind of range because it's not an exact science. What about a metabolic alkalosis? Well, in a metabolic alkalosis, the bicarbonate rises, and so does the PCO2 in response. Not enough to balance out the pH perfectly, but some. And this is described by this formula. The PCO2 that you expect should be 0.9 times the bicarbonate plus 16 plus or minus 2. This calculation is not as accurate as Winter's formula because it's restricted by hypoxemia. The PCO2 seldom rises all the way because when you start hypoventilating, you start getting hypoxic, and that begins to make you breathe, and so the PCO2 is not as accurate in this case. So here's an example. If the plasma bicarbonate concentration rises to 36, the PCO2 should be 0.9 times 36 plus 16. In this case, it would be 32.4 plus the 16 equals 48.4 with the range of 46 to 50. Again, that range around 3 to 4 gets you in the ballpark. In acute respiratory alkalosis, what's happening is you're breathing quickly, and you just started. You're breathing fast, it's kind of cool. You drop your PCO2, you drop your hydrogen ion concentration in your blood. As a response, because of the gradient, hydrogen ion concentration leaks out of the red blood cells into solution. When it does that, it encounters bicarb that's in the solution, and through the action of carbonic anhydrase right here, turns into carbon dioxide and water. Those are the things that you breathe out. This is called buffering. And what happens in buffering is that in acute respiratory alkalosis, as a result of this buffering that is just described, for every 10 millimeters of mercury decrease in the PCO2, there is a 2 millimeter decrease in the plasma bicarbonate concentration, as seen right here. It's a 10 to 2 ratio in acute respiratory alkalosis. In chronic respiratory alkalosis, the kidney starts to get active. In this case, again, you're breathing quickly all the time. It's a long time. And what happens is the compensatory response is decreased by. In this case, the usual mechanisms that lead to bicarbonate reabsorption are turned off, and bicarbonate is lost in the urine. So in chronic respiratory alkalosis, as a result of renal compensation, not cell buffering, but renal compensation, for every 10 decrease in the PCO2, there is a 4 milliequivalent per liter decrease in the plasma bicarbonate concentration, a 10 to 4 ratio. The kidney is stronger than the red blood cells in this case. In acute respiratory acidosis, what happens is your PCO2 rises. And when that happens, the ratio goes up and you get an acidemia. in this case, when the PCO2 hits the blood, it does the reverse of the reaction I showed you before, and carbon dioxide and water, through the action of carbonic anhydrase, turns into the hydrogen ion concentration of bicarbonate. The bicarbonate rises in the blood, therefore mitigating this rise in the ratio, and the pH goes down. This is buffering for acute respiratory acidosis. In this case, due to this process, there's actually an increase in plasma bicarbonate, averaging 1 milliequivalent per liter for every 10 in the rise of PCO2. You can see that ratio here. In a chronic respiratory acidosis, again, the kidney gets into the business of doing that. As the PCO2 stays chronically elevated, the things that tend to cause bicarbonate reabsorption are absolutely jacked up, increased, and so in this process usually takes a few days, 3 to 5 days, and the ratio is a 3.5 milliequivalent increase in the plasma bicarbonate concentration for every 10 increase in the PCO2, and here it is. These are things that you can memorize, and you might want to try to do that. They differ between labs. Sometimes you see different values. They're often in this range. During the exercises that we're going to do in academic half day, we'll have a card for reference so you don't have to memorize these things. Step 7, calculate the delta-delta. The delta ratio is sometimes used in the assessment of an elevated anion gap metabolic acidosis to determine if a mixed acid-base disorder is present. So you tend to use this in increased anion gap metabolic acidosis. Simply stated, the delta ratio or the delta-delta is the ratio of the increase in the anion gap to the decrease in the bicarbonate. So let's take an example. Imagine if you lose bicarb for a reason. Maybe you have lactic acidosis, and your bicarb falls by 10. When that happens and it's replaced by another negative, the anion gap is going to go up by 10. But it's not that simple, because what happens in bone is that the hydrogen ion concentration is elevated, it goes into the bone, and there's buffering, and so some bicarb leaches out of bone, and maybe in this example it goes up by 3. So the total loss of bicarbonate is 7, 10 minus the initial 10 drop plus the 3 that you gain from bone buffering. The anion gap, though, still resides at 10. So in this case, if you did the delta anion gap, which is 10, and the delta bicarb, which is 7, you get at this ratio. So the elevation in the anion gap usually exceeds the fall in the plasma bicarbonate in lactic acidosis. And the delta-delta, when you do this ratio, is usually 1.6 to 1. Let's take another example. Imagine you have a case of diabetic ketoacidosis in which there's a bunch of ketones hanging around, and so the bicarb is buffered, say at a negative 10. When this happens, the anion gap is going to go up by 10. Also imagine that this person is having diarrhea, and instead of buffering a little bit of bicarb, they're losing it out the gut. In this case, because of the theory of electroneutrality, chloride is going to go up by 5. But if you look at the total amount, the total bicarb is down 15, and because of this retention of chloride of plus 5, the anion gap is only 10, so a ratio of 10 to 15. A delta-delta value below 1 indicates a greater fall in the bicarbonate, right here, that can be explained by the increase in the anion gap. In this situation, the additional fall in bicarbonate is due to further buffering of an acid that does not contribute to the anion gap. And for example, the addition of hydrochloric acid to the body as a result of diarrhea. So this is how you diagnose a non-increased anion gap metabolic acidosis when the delta-delta is less than 1. One final example, take the case of DKA where you, again, buffer bicarb. In this case, I have an example down by 10, which increases the anion gap up by 10. But this time, instead of diarrhea, the person's having vomiting, which is also very common in DKA because they get belly pain and they throw up. In this case, you're losing chloride out the body, and when that happens, the kidney says, well, I've lost a negative, I'm going to retain a negative, and often it retains bicarbonate at the kidney, and that's a plus 5. In this case, the total ratio of the anion gap is 10, but the change in the bicarbonate, because it's 10 minus 5, is 5. So a value of 2 to 1 in the delta-delta indicates a lesser fall in bicarbonate than one would expect given the change or the increase in the anion gap. This can usually be explained by another process that increases the bicarbonate, in other words, a concurrent metabolic alkalosis. So when you have a metabolic acidosis, when the delta-delta is greater than 2, you might have also a metabolic alkalosis. One caveat to consider, though, is if you have a pre-existing very high bicarbonate level, as you see in chronic respiratory acidosis, you can kind of get messed up on this calculation because it hasn't fallen as far, and you might see this high ratio and mistake it. So don't forget about that as well. Well, let's put it all together and solve some acid-base problems using these 7 steps. A 36-year-old man is found down near a bottle of rubbing alcohol. Now we know that rubbing alcohol is on the list of things that causes an increased anion gap metabolic acidosis, so that's what I'm thinking about in step 1, which is the presentation. Step 2 is to calculate the Cassirer-Blake equation. In this case, we have the hydrogen ion concentration equals 24 over acid plus base. As you can see here, let's just plug those numbers in. That the hydrogen ion concentration is 80 minus the last 2 digits of the pH, 7.28. That's what it should be at 52. Well, the question is, does 52 equal 24 times acid, that's the PCO2, over base, 12, that's the bicarbonate? And the answer is, it does. That works out perfectly. If you get your calculator out, it works. The next is to calculate the gaps. So what is the anion gap here? The anion gap is 25, which is quite elevated. I then draw the arrows. So let's do that. You have a pH that's down, a PCO2 that's down, a bicarbonate that's down, and an anion gap that's up. So when I'm looking at this, I see 3 downs all in a row. I'm starting to think, well, at the very least, I probably have a metabolic problem because they're all in the same direction. So I'm going to apply and choose a rule of compensation. I might as well choose a metabolic rule of compensation because I have a high anion gap and a low bicarbonate. I'm thinking maybe this is an acidosis. I'm going to apply Winter's formula, which is the PCO2 that you'd expect should be 1.5 times bicarbonate plus 8 plus or minus 2, the famous Winter's formula. So let's plug those numbers in. The question is, 26, which is the PCO2 that we see, is that 1.5 times 12, which is the bicarbonate, plus 8 plus or minus 2? Well, it comes out, it does. It's exactly 26. So the answer is yes. So this looks like it's a pure increased anion gap metabolic acidosis. You might want to go one more step and calculate the delta-delta to make sure there isn't something there. So let's do that. We don't think it's mixed. So let's calculate the delta-delta. That's the change or the increase in the anion gap over the decrease in the bicarbonate. Well, the anion gap was 25, normal is 12, so that's 25 minus 12. The bicarbonate was 24, now it's 12. So the ratio there is 13 divided by 12, and that's 1.08, which is pretty close to 1. In this case, I don't think there's an underlying metabolic alkalosis. So to solve this problem, what we have is an increased anion gap metabolic acidosis with appropriate respiratory compensation. If you can do this correctly, you can say all these words without extra words, saying only what you mean, getting the exact right diagnosis. Example problem number 6. A 22-year-old ballerina with recent rapid weight loss. Now, for step 1, presentation, a couple of things that ballerinas might do to lose weight. They might take diuretics, sometimes they take laxatives, and those might cause 2 different things, so I'm thinking about each of that. A laxative might cause a non-increased anion gap metabolic acidosis, whereas a diuretic might cause a metabolic alkalosis. So we'd have to figure out which one this person has. Well, let's solve the Cassirer-Blake equation. As you see, this equation again is hydrogen ion concentration equals 24 times acid over base. In this case, what you'll see is that you take 80 minus the last 2 digits of the pH, which is 50. The hydrogen ion concentration should be 30. In this case, the question is, does 30 equals 24 divided by acid, 46, which is here, base, 38? Does that equal? And the answer is, that's 29.05. It's pretty close. We'll give it 30. Step 3 is to calculate the gaps. In this case, the anion gap is 12. There is no anion gap. Step 4, my step is to draw the arrows. So increased pH is up, so that's an elevated arrow. PCO2 is elevated, 46. The bicarbonate elevated at 35. And as I said, the gap hasn't changed. So now you've got 3 things all in one direction. Again, it's an alkalemia plus metabolic. That's all in the same direction. So I got to pick a rule of compensation. In this case, I'll pick the other formula, which is the PCO2 equals 0.9 times bicarbonate plus 16 is the PCO2 that you would expect to see. So what we see is 46. Does this equal what we expect to see? So 0.9 times 35, which is the bicarbonate, plus 16 comes out to 47.5. That's within 3, so this would be a yes. Is it a mixed acid-base disorder? This would say not. And there's really no reason to calculate the delta-delta here because In this case, it's not an increase in anion gap metabolic acidosis. If you did it, you get some weird number. It's 0. It doesn't give you any help at all. So that's example problem number 6. The answer here is a metabolic alkalosis with appropriate respiratory compensation. Example problem number 7. A 74-year-old with congestive heart failure presenting with hypotension and pulmonary edema. Well, step 1, presentation, I'm thinking, goodness, heart failure, you got hypotension, what usually leads to acidosis because of decreased perfusion, usually through lactate. You got pulmonary edema, kind of depends. If he's breathing real fast, he could have a respiratory alkalosis. If he's really underbreathing, he could have a respiratory acidosis. So those are 2 things I'm thinking about when I hear this case based on presentation. Solving for Cassirer-Blake equation, same thing as before. You've got the hydrogen ion concentration. In this case, 80 minus the last 2 digits of the pH. Here it's 7.39, 41. The question is, does 41 equal 24 times acid over base? In this case, the answer is 41 equals 40. So yes, we will accept this as something we can keep going. If we calculate the anion gap, this anion gap is 23, which is elevated. I'm going to draw the arrows. In this case, interestingly, the pH is normal. Like I said before, if one value is normal and the others are abnormal, you probably have a mixed acid-base disorder. So that's what we might be looking at here. The pH, PCO2 is down at 25. The bicarbonate is down at 15. And the anion gap is elevated. So we have to choose a rule of compensation. We have a normal pH. We have an anion gap that goes up that tends to only happen in metabolic acidosis. So the rule of compensation that I'm going to choose in step 5 is going to be Winner's formula again. And when I apply Winner's formula, I'm asking, does the PCO2 that I see, 25, equal 1.5 times bicarbonate plus 8? In this case, it doesn't. What I'm calculating is 30.5, and what I'm getting is 25, and that's too far outside the range. So in this case, I'm thinking maybe this is step 6, this is mixed, because the actual bicarbonate at 25 is lower than the predicted bicarbonate. And when the actual is less than predicted, and what you're doing is less than what it should be through compensation alone, that is a second acid-base problem. That is respiratory alkalosis. We can do the delta-delta here because it is an increase in anion gap metabolic acidosis. So what you notice is the decrease in, or the increase in anion gap went from 12 to 23, 23 to 12. The decrease in bicarbonate, 24 to 15. That's a ratio of 99, so it's 1. So there really isn't anything hidden here. It's what it should be. I'm not too concerned about it. So this example problem answer is a mixed increased anion gap metabolic acidosis and a respiratory alkalosis. Example problem number 8. A 24-year-old diabetic admitted with persistent vomiting, polyuria, and thirst. So I got a young diabetic with vomiting, polyuria. I think this is going to be DKA. That's what I'm thinking. There are lots of things that go on with DKA, and it's often a mixed acid-base disorder. So I'm thinking that that's probably what we're dealing with here. If I solve for Cassirer-Blake equation again, you take 80 minus the last 2 digits of the pH. It's right on the edge here at 7.20, but we'll take it. It's the hydrogen ion concentration would be 60. If we ask ourselves, does 60 equal 24 times 25 divided by 10? In fact, it's exactly 60. So this we can continue because you can solve for the Henderson equation. Are there gaps here? Yes, there is. The calculated gap here is whopping 40. It's big. If you draw the arrows, what you get is a pH that's down, a PCO2 that's down, a bicarbonate that's down, and a gap that's up. So you see this. You see all the things, all the arrows in one direction. For the pH, the PCO2, and the bicarbonate, you're thinking, I got to apply a rule of compensation, go to the old standby, Winner's formula. In this case, your question you're asking is, does 25 equal 1.5 times 10 plus 8? And it turns out to be 23. So yes, there isn't anything funny here. What you have is appropriate respiratory compensation. But is it mixed? Should you do the delta-delta? Well, if you do the delta-delta, what you find is the change in the anion gap is 40 minus 12, and the change in the bicarbonate is 24 minus 10. In this case, the ratio is exactly 2, which indicates an underlying metabolic alkalosis, which is a very common acid-base disorder that people with DKA get. So this is an increased anion gap metabolic acidosis with appropriate respiratory compensation and a metabolic alkalosis. Example problem number 9, a 58-year-old man with diarrhea. Step 1, the presentation here, diarrhea often causes a non-increased anion gap metabolic acidosis. That's kind of what I expect. Let's see what we get. If you apply the Cassirer-Blake equation, you'll see that the hydrogen ion concentration is 80 minus the last two digits of the pH, 34. That's what you expect is 46. The question is 46 equal 24 times acid, 34 here, over base, 18. In this case, the answer is it's 45.3, so that's pretty good. We'll keep going. Are there any gaps? In this case, there's no anion gap. It's just 9 here. The arrows here, you draw the arrows, you notice the pH is down, the PCO2 is down, the bicarbonate is down, the anion gap is not in play because it's normal. So you got 3 things all in a row. You've got a low pH. The question is, what's happening here? Is this just another metabolic acidosis? So in this case, you do the Winter's formula, and you find that the question you're asking is, does 34 equal 1.5 times the bicarbonate, in this case 18 plus 8, turns it to be 35. Yes, it looks like it's doing just fine. You're asking, is it mixed? It's not mixed by this, but should I check the delta-delta? In this case, what you'll find is there's no increase in anion gap. There's no reason to do it. And so this is really just a non-increased anion gap metabolic acidosis with appropriate respiratory compensation. I hope you've enjoyed and gotten something out of this acid-base tutorial from the University of Cincinnati. If you want to see other videos in this series, you can go to YouTube and hit the keyword INTMED, and you'll find our YouTube channel with our many videos there. Thanks for watching.